So in this video, we will introduce reinforcement learning. And reinforcement learning is definitely a natural conclusion to the topic of planning with interaction, and definitely follows after the series of videos that we have developed on Markov decision processes. As in MDP, we have been assuming full knowledge of the problem dynamics and reward functions. And over here, we'll start removing that kind of assumption, and we will be called to estimate those quantities from experiences. So some of these experiences initially will take the form of sampling. So we'll look at the Monte Carlo methods and the temporal difference type of methods as two instances of sampling. And then we will introduce a flexible approximation to those estimates in the form of neural networks and conclude the discussion with deep reinforcement learning. Like we have done in the MDP, also in reinforcement learning, we will divide, if you like, these considerations into two steps. One is the so-called prediction step, where our job is really now to estimate the corresponding value functions, either the V functions or the Q functions. Now, because these functions are going to assume no knowledge of any model dynamics and therefore will be estimates, we need to learn them. The learned functions are typically denoted with capital letters instead of small letters. So we will be using capital V and capital Q for those. So, and we will start with what is actually called the first one method, which is called the Monte Carlo. Or MC method for the prediction problem. All right, so according to this kind of method, and just a recap, from the other video, when we were looking at the MDP, we had this equation for the V function, that's a small v, of the for every state S. And this is an expectation over all policies of the returns from that kind of state, which is the return GT, given that we are in state S. Okay, and as a kind of reminder, the policies, we have plenty of policies that are in any problem. Like, let's say, for example, we have 1, 2, 3, 4, 5 states. And let's say if we had 2 actions per state, either left, let's say, or right, then we could have here 2 to the power of 1, 2, 3, 4, 5, 2 to the power of 5, or 32 policies. 32 possible policies. In general, we will have as many as the cardinality of the set A of actions to the cardinality of the set of states. So as you can understand, the number of policies that exist in any MDP problem is actually could be quite large, and therefore one other reason why we are actually looking at these approximations here later on is to make sure that we're converting an infeasible to be solved problem into a problem that can be reasonably expected to be practical and feasible to solve, with those approximations. So back to the sort of Monte Carlo kind of prediction problem. This was when we knew the dynamics, and therefore what we were doing there is to do actually a one-step, the so-called Bellman expectation kind of backup, where for every action we were ended up in some state S prime, the next state, and this was effectively after the action is taken, we were migrating to S prime and we were recovering some kind of reward. And of course, the policy was responsible for transitioning, for taking, if you like, those one of the available kind of actions to us from that state S. And so the so-called estimate of V pi of S ended up with a Bellman equation expectation equation. If you like, that was basically the dynamic programming, the so-called dynamic programming solution. Ended up being a kind of a bootstrapping equation, and we call that bootstrapping equation the fact that we were using the v pi of s prime to calculate the v pi of s. And if I trace back that specific equation, we call this iterative policy evaluation when we were discussing in that video the MDP policy evaluation for state value functions. Of course, we have an equivalent one for the Q functions there. And actually, you can see very clearly that the Vk of S prime over here is actually being used to calculate the updated value function for the state S. And this is basically what we call by bootstrapping. In essence, we are suggesting that I don't have to, in order to calculate all this kind of averages, I need to just know the value function of these successors kind of states in order for me to calculate this one. And I don't need to expand all the way into the diagram, because in the, effectively, this state at some point it was calculated. It took the S32, for example, took the place of S33, and it was itself evaluated at some previous kind of iteration. So we are pretending that S32 is the kind of a sort of root state over here, but effectively what we did, if you recall, was to evaluate all states. Okay, so all states, these V's are now vectors, and they are evaluating all states at the same time. Okay, so that's basically what was the bootstrapping, and equivalently, we can actually see a diagram over here just to that kind of demonstrates that kind of what I just said. With dynamic programming, we have full expansion, very wide expansion of the tree, where at the root of the tree is a state that we are evaluating the value function of. And here we are bootstrapping that value from the successor states, as we just discussed. And the intuition behind this, and obviously in the dynamic kind of programming, the whole intuition is that you can always start from some kind of a simple problem where, let's say, you are kind of close to some kind of a terminating kind of state that you kind of know the reward, and there is, because it's terminating, you are not interested on any future rewards. There's no such future, if you like, for you. And then you can, if you know the value functions of these kind of states, you can calculate the value functions of the states which are above you, and via the kind of a bootstrapping method. And then you're going into more and more larger and larger kind of problems, for more and more difficult problems than what you started with. But as I said, in reality, we are not breaking down the problem into sub-problems, but we are iteratively solving this Bellman equation, iterative policy evaluation based on Bellman equation. Now, in Monte Carlo state value prediction, what we will do, since we don't have the dynamics, and effectively the dynamics are actually were used to calculate the sort of the bootstrapping and the previous, in the case of dynamic programming, the value function. What we're actually going to do over here is we are going to sample to create, if you like, experiences. And the assumption here is that we can, first of all, that we have, if you like, a simulator that will be able to sample experiences from the system. So the model is being used only at a sampling level to generate these experiences, and it is a much, much easier sort of proposition as compared to estimating these models or learning, if you like, the model dynamics. And so what we will do is, for every state and also state and action pair that we are using for the V and the corresponding Q functions, what we will do is we'll keep scores. What are those scores? As what are the returns that we have experienced after those states. And keeping a score of this kind of states, then it will allow us to calculate the value function, as we'll see. Another distinguishing factor over here is that in order for us to get to the sort of sample return, we will need to reach, if you like, the terminating state, and therefore we are talking about and sort of generating kind of episodes of of some kind of length, and then we will be able to retrieve those returns per episode, and then average across many thousands of episodes in order for us to be able to approximate as much as we can the true value function. So effectively, we are going to be approximating, and let me make this kind of, as I reach the end, the terminating kind of state. We are going to be approximating this expectation over here with the many trajectory sums, like averages across many trajectories. And let's call this the return across each trajectory, starting, let's say, from the moment that we were in state t, in state s at time t. Let's say this will be the return on trajectory. Let's call this trajectory tau. Also, trajectory is a term which is used extensively in motion control, but a synonym of that is the episode, which is a bit more common across reinforcement learning. So on that kind of episode tau, we will have some kind of a summation of the discounted. So k is equal, let's say, to 0 to t minus capital T minus 1. Let's assume that this is the length that this trajectory kind of lasted of all discounted kind of future rewards. Okay, so this is going to be the return, and then what we'll do now is we'll write the update kind of method, the update kind of formulation for each of the elements of the state value function. So the first step is that, for each time step, t that S is visited, in an episode, we keep this score via this kind of counter, increment the counter n of S, that effectively counts the visitations, the number of visitations in that kind of state, and calculate the total return as G capital T of S is equal GT of S plus GT. And effectively, the second step is that at the end of thousands is an example, many, I will call it episodes. The value, we calculate the estimate, which is now capital V, as we said, capital V of S, it is G T of S divided by N of S. And as the number of times that we are N of S is visited is becoming larger and larger, then we will effectively converge this as N, in other words, of S tends to infinity. This will converge to V pi of S. Okay, and I think I've forgotten to add the pi over here in the capital V. And we also do the following trick called incremental mean, sample mean, or mean approximation. Where I think this is exactly the same trick that we had done in another video when we were dealing with recursive state estimation and kind of a Kalman filters, where we are effectively writing a statistic in a kind of recursive form. The same thing can be done in either the mean or the covariance or correlation matrices. Here is just to remind everyone, we can actually write the sample mean of the kth sample that is actually coming in from 1 to k as 1 over k of summation from, let's say, j is equal to 1 to k, xj. Let's say the xj was a sample. All right, and then we have, can write this as 1 over small letter k of breaking down the sum into j is equal to 1 to k minus 1, xj plus xk. And then if we do another step, we will be able to write this as the previous mean, mean estimate plus 1 over small letter k of xk minus mu k minus 1. So the previous estimate plus 1 over k, the current sample minus the previous estimate. And back then in that kind of other video, we actually call this some kind of indication of the Kalman gain, if you recall, and all this kind of stuff. So it's exactly the same formula. And if you use this actually formula over here, we'll be able to do the sort of the value function with the Monte Carlo method. Can be written as n of s, these two steps, is equal to n of s plus 1, incrementing, if you like, the counter every time we visit state s. Okay, and the second is to calculate the v of s, let's say v pi of s, is equal to v pi of s plus, let me call this alpha gt, which is the current return as it is estimated for that specific episode, minus v pi of s. So so this is the previous estimate. These are the previous estimates. Now, obviously, we can distinguish there with the an index k, but in implementation, you have a left-hand side and the right-hand side to be sort of separating them in a let's say implementation in software. So you don't need to necessarily to put the indices. So alpha in this case is 1 over n of s. And this, we can call it the forgetting factor. And obviously, this forgetting factor is less than 1. This allows us to have a bit more flexibility on how many terms we're able to average. And we can actually call this implementation the running sample mean of the state value function. It's also worth noting a couple of things from this kind of formula. The first is that the estimate, there's no bootstrapping. In other words, we do not use an estimate of the value function of another state. So there's no bootstrapping here. And as effectively the estimates between states are kind of independent of each other. And this is also kind of an advantage because computationally wise, we can actually, in any problem that we have, to estimate value functions for a subset of the states or even just a single kind of state, we're able to do so with Monte Carlo methods. And the second is that the value function can only be updated at the end of each episode, because this is emphasis on only, because this is basically where we get that kind of return. And this is basically something that we will work to kind of provide an enhancement on that with the temporal difference methods. Now, as an example of what is actually called also a simple example where we don't have any explicit kind of actions over here or decisions, where this is actually called Markov reward process. We have a kind of a straight line kind of sequence of states where the agent may start from a state over here, shown here, A, B, C, D, E, and there is actually this is a one-way arrow, goes into a terminating state on the right hand side, where the reward over here is 1, it's a terminating state. All of the other rewards are actually 0, and actually the agent starts with C, that's a starting state of the agent, and there is a left terminating state as well that is also express reward of 0, but over here in that right terminating state we have a reward of 1. And we would like to come up with the state value function estimate using, let's say, first kind of a dynamic programming. And what we will do is we will use the formula, let's say V pi of S is summation over, let's say, actions of the policy of A given S. Over here we have two potential actions that the agent can take. Either we go left or right at every state. So these are the general formula, but it has to be kind of specialized to there's a transition model, as we said, and then we have here R plus gamma V pi of S prime. This was the kind of the bootstrap. This is a dynamic programming solution. And gamma here is also equal to 1. All right. So effectively, so agent also need to write out also that agent can go left or right. One state at each step with equal probability. Okay, all right, so that's basically the policy. So this is, let me call it pi of A given S is 0.5 for left and 0.5 for right. All right, so I can actually take now each of these possible states and actually write down what will actually be that formula will actually tell us. So this will be, and this is also the, before I do so, I can actually also write the kind of a backup diagram. For every state S, I have two actions, either left or right, and for each action I may end up in potentially in two neighboring states, sometimes only one because it's terminating, but that's basically in general the backup diagram. This is the S prime. This is the transition model here. P of S prime comma R given S comma A, and this is the policy pi. Okay, so this is so according to this formula, V pi of A, S will be A, is going to be from A I can actually go right or left. So if I go left, I will have here, I can go left with probability 1/2, and over here I can actually have the immediate reward go left will actually be 0, will be 0 plus gamma, which is 1 VP of T, let's call it L, let's call this TL, and this call this TR for right. Okay, so plus, and the other one is 1/2 of 0 plus VP of B. That's the other action, and this will actually be, since the VP of TL is 0, this will be V pi of B over 2. Okay, that's kind of equation 1. The V pi of B will be, I'm going to write now quicker, V pi of A plus 1/2 0 plus V pi of C, which is V pi of A plus V pi of C over 2. That's equation 2. And then we have V pi of C is equal V pi of B plus V pi of D. Now I think everything is clear. Over 2, equation 3. V pi of D is equal V pi of C plus V pi of E over 2, 4. And finally, V pi of E is equal V pi of D plus 1, which is coming from the fact that we are going into TR, divided by 2, and that's equation 5. And it's easy to solve this problem. From 1, I can have that V pi of B is equal to 2 V pi of A. From 2, I have that 4 V pi of A is equal V pi of A plus V pi of C. In other words, V pi of C is equal 3 V pi of A. From 3, I have V pi of D is equal 4 V pi of A. And from 4, I have V pi of E is equal 4 V pi of A. And from 5, I have V pi of A is equal to 1 over 6. And therefore, I'm able to solve all of these other expressions. This is going to be 4/6 or 2/3 V pi of A. 2/3 V pi of A. And this will be 1/2. I'm sorry, this is just 2/3, not V pi of A. Just 2/3. This is is 1/2, and this is 1/3. Okay, so that's basically 1/6, 1/3, 1/2, 2/3, and that's 2/3 also. Okay, and that's basically the solution of the value function as a vector of across all states. I make a mistake over here. It's this 2/3 plus 1/2, which is 5/6. Okay, so that's the vector of solutions. And what we will see with Monte Carlo, I'm just going to show you the graph of, which is basically the left side kind of graph here. What we will see with Monte Carlo is that we are going to, this is basically what we estimated, the black line over here for all the states. This is basically the true values from the dynamic programming solution. And what the Monte Carlo actually will start is, we'll start with some kind of initial kind of vector of values, and it will start trying to estimate the value function based on a number of trajectories with this averaging, the running average that we have just discussed. So this is with one trajectory or one episode, 10 episodes the green line, and the 100 episode estimates are the ones which are obviously going to become closer and closer into the true value function.